Hello. In this video we're going to go over numerical techniques in MATLAB. In particular, we're going to go over interpolation and curve fitting. Here's an overview of the topics we're going to go over. We're going to start with interpolation in MATLAB, and then we're going to move on to curve fitting and examples on each. Interpolation is the estimation of values between data points. So, for example, if you're given a set of data points that is fixed, and you're interested in estimating the values that are between these data points, then interpolation will help you do that. We're going to understand it further later on once we move on to examples. In one-dimensional interpolation, which we're going to focus on, each point has one independent variable, for example x, which is the x-axis, and one dependent variable, which is y, which is going to be the y-axis value. One-dimensional interpolation in MATLAB can be done with the function interp1, which has the following form. So here, x and y are the horizontal and the vertical coordinates of the data points that are given, such that x is the independent variable and y is the dependent variable. So we can say that the function is y of x. Y query is the interpolated value. We use yq for short. And x query or xq is going to be the horizontal coordinate of the interpolation point, which is the independent variable. So if you're interested in finding the corresponding value, the yq of xq, of the given xq, then you'll use this form. And finally, the last input you need to pass is the method of interpolation. By default, MATLAB assumes linear method. So if you do not put the last argument here, MATLAB is going to assume you want to do linear interpolation. Now we're going to do an example that illustrates the concept of interpolation without the help of MATLAB. So given a set of data points, x and y, it's possible for us to estimate the values in between these data points with the help of interpolation. For example, if we're interested to find the corresponding value of y for x is equal to 1.75, the first step to do is to figure out the nearest 2 points for x is equal to 1.75, which turns out to be x is equal to 1 and x is equal to 2. So we can assign these points names, for example, x1, y1, x2, y2. Next, we can apply the formula for linear interpolation and plug in the values for y1, y2, x1, and x2 to obtain y for the given value of x. Another way to do it is using a graph, so we can plot these points on the graph and then connect the points using straight lines, hence the word linear. So after that, we can draw a line on the point x is equal to 1.75 and find the intersection point to figure out the result. Let us do it mathematically. Here we can just simply plug in the values. Y is equal to 2 plus 4 minus 2 divided by 2 minus 1 times 1.75 minus 1. If we continue with the computation, we're going to end up with 2 plus 2 times 0.75, and then 2 plus 1.5, and then 3.5. So for x is equal to 1.75, using linear interpolation, we figured out that y is equal to 3.5. This is all done without the help of MATLAB. Now we're going to do the same example, but with MATLAB. So we're going to use the interp1 function. We're given the same set of data points, and we want to figure out what is the value of y for when x is equal to 1.75. The first step is to create an array that includes x, so x is equal to minus 3 increment by 1 until we reach 3. And then since y is kind of random for us for now, so we're going to store it manually into an array named y, y is equal to 6, 4, 2, 0, 2, 4, and then 6. Now we're going to create a variable named xq in which we're going to store the value 1.75. Since we've already used a variable named x, for the given data point, we're going to use xq or xquery. Next, we can find out yquery as the interp or the interpolation. We need to assign these inputs in the correct order. So the independent variable first, then the dependent variable y, and then finally the point of interest, which is xq. After we hit enter in MATLAB, we're going to figure out that yq is actually 3.5, which is similar to what we've obtained earlier. If you do not specify a method of interpolation when using the function interp1, MATLAB is going to assume you want to use linear interpolation. But there are other methods of interpolation that includes the nearest neighbor interpolation, the spline or piecewise cubic spline interpolation, and the p-chip or the shape preserving piecewise cubic interpolation. There are other methods that are not listed here, but you can find them out by typing help interp1 in MATLAB. Basically, you use the best method if you know some information about the original graph of the function. So if you know for sure that the function is linear, it's best to use the linear method. If your graph looks something like the one in the middle here, you're going to use the nearest neighbor, or if the original graph for your data points is curvy, such as x squared plus something, for that specific case, you're going to use the cubic or the spline interpolation method. Here's another example of interpolation using MATLAB. Basically, we created an array named x, starting at 0, incrementing by 1 until we reach 4, and then y of x, or the dependent variable y, is equal to the square root of x. Then we changed our mind such that we want to use different data points, such that instead of having an increment value equals 1, we want to create a new array named x new that starts at 0 but increment this time by 0.5 instead of 1 until we reach 4. Then we can reevaluate y new by using interpolation or one-dimensional interpolation. As defined here, we've used the spline method because the function is not linear, and the rest is just verification or just for us to visualize the result. I've calculated the exact value of y for the new array x new by using the square root function again, and then I finally used the table method in MATLAB to just display the data as a table. The first column you see the x values, the independent variable. The second column you see the exact value for the function the square root of x, and then the last column is the approximation of the square root of x using interpolation of method with the method spline. Notice how the exact versus the approximation are very close to each other, which means we've made a good estimate. Now we're going to move on to a new topic, which is curve fitting. So curve fitting is the process of fitting a function to a set of data points. So we have a data points, but you want to create a model that represents them. And then using that model, you can, of course, create or estimate new values between the given data points. The function can be used as a mathematical model, as I just mentioned, and there are different types of functions, as we know: linear, polynomial, power, exponential, etc. Therefore, curve fitting can be a complicated process. But the simplest function is a linear function that can be simply represented by a straight line. Observe that some of the data points that are given already or known will not fit in the estimated line, but it will be close enough for our purpose. Curve fitting with polynomials in MATLAB can be done with the polyfit function that uses the least squares method, meaning the function aims to minimize the sum of the squares of the vertical distances between the data points that are known already and the model itself. The function has the following form. So basically, x and y are the horizontal and the vertical coordinates respectively of the given data points. So x is the independent variable and y is the dependent variable. And here is the degree of the polynomial for the model you want to figure out. And p is a vector containing the coefficients of the polynomial that fits the data. After creating a polynomial model for the data points using the polyfit function, you can use the polyval function to evaluate the given polynomial at a specific point. The polyval function has the following form. P is the vector containing the coefficients of the polynomial, which can be obtained from the output of the polyfit function from the previous slide. And then xq or x query is the horizontal coordinate of the point, which is the independent variable. And then y query or yq is the value of the polynomial at point xq. Now we're going to do an example on curve fitting without MATLAB to better illustrate the concept of curve fitting. So given a set of scattered data points x and y, we can estimate the equation that represents these data. The first step we can do is to draw a graph by just simply eyeballing it, such that the graph will connect the data points together. With the help of the estimated model here, we can figure out or find out the estimated value for other points that are not known in the set. For example, we can figure out the value of y for x is equal to 0.5. And we can do that by drawing a line, a vertical line at x is equal to 0.5 and finding the intersection point between the line that we drew and x is equal to 0.5. So for that, we can estimate that y at x is equal to 0.5 is approximately 12.8. Now we're going to do the same example we did earlier, but this time with the use of MATLAB. Remember, MATLAB is going to give us a better estimate since it uses the least squares method rather than just eyeballing a graph like we did in the previous slide. So given the same set of data points, we want to figure out the value of y when x is equal to 0.5. We're going to start by creating an array named x in which we're going to store the values of x, starting at 0, ending at 5, incrementing by 1. Y is an array that has the values 15, 10, 9, 6, 2, and 0. The first step is we're going to choose the order of the polynomial. We want to assume polynomial of order 1. And next, we'll use the polyfit function on x, y with the order of 1, and p is the output of the polyfit function, which is of course the coefficients of the polynomial. Remember to always use polyfit with that specific order, so you always put the independent variable first, then the dependent variable, and finally the order of the polynomial. So given the values of p, we can create a model or use these coefficients to write an expression that represents the data points that are given. So you can rewrite or write the model or express it as minus 2.91 times x plus 14.286. So we can estimate the value of y for a specific x using the polynomial or the first order polynomial that we just figured out. Now, instead of plugging the values manually by hand, we can use the polyval function to figure out the value of y at x is equal to 0.5. So the first step we did here is to create a variable named xQuery or xq, in which we stored 1/2. And then we can figure out that yq is equal to polyval. First, you need to provide the polynomial coefficients and then provide the x value you want to find the y value for. So that means that y at 0.5 is estimated to be 12.829. Here you have an exercise that is an application on what we've learned in this video. We're going to solve this exercise together in the live session. Feel free to pause the video and read the question and try to solve it on your own. Thank you for watching. If you have questions related to the lab topics, please use the discussion forum on Moodle or email me at alt@auk.edu.kw.